It is my special pleasure to introduce Mario Carpo. I'm a bit of a fan of his works, and I think they have impressed many of us and influenced us in our own projects. He's the Rainer Benham Professor of Architectural History and Theory at the Bartlett School of Architecture in London. His research and publications focus on the history of early modern architecture and the theory and criticism of contemporary design and technology. He has published a series of influential books, starting with the architecture in the age of printing and including The Alphabet and the Algorithm, Second Digital Turn, Beyond Digital, Design and Automation at the End of Modernity, all published by the MIT Press. Today he's going to talk about AI tectonics. I'm very curious how we will learn about generative AI and how this influences the way we design, imagine, imitate, and possibly also build new architecture. Floor.
Thank you. Can you hear me? Good. I changed my glasses to read my paper, which means that I don't see you anymore. That's irrelevant, since I don't need you right now. So, thank you to David for the introduction, and thank you to David, Selen, Ina, who guest edited the issue of AD, to which I was happy to contribute. That's the reason I'm here. Thanks for the organizers for bringing me here yesterday with a cab from Linate, because I hurt my knee, so I cannot walk that much. So if you see that I'm stumbling at some point, that's the reason. Don't worry, it's possible. But and I'm sorry I couldn't follow part of the day, because since this morning I was on a split screen. Part-time I was here, and part-time I was in the hotel room now at the Albergo Milano, watching CNN, and realizing that I should have changed at least a few parts of my paper based on what happened last night, because I realized that most of the things we care for as designers, things, ideas, principles, sustainability, for example, which is the main topic of the event. Many of these things, sustainability and many others, of course, have just been voted out of a huge slice of the world market, which means with a huge consequence for sustainability for the rest of this vast planet. So this is something I did not anticipate when I was writing this paper, and I didn't have the time to change it, to take this change into account. But nevertheless, let me start from a recollection of things as we often do when things don't go very well. We start from recollecting things that happened a long time ago. And for example, who remembers, talking about the good old times, who remembers the 90s? I do, because I'm old. But most of my students were not even born back then, so I cannot remember the impression that this building made when it was inaugurated in the fall of 1997. But I do remember the shock that many of us felt when we realized that this was the demonstration that with digital technologies we could do stuff which up to that day could have been imagined but could not have been built. But for those who, like me, are old enough to remember the spirit of that distant time, even more distant since last night, They will remember that the rise of digital technologies in the 90s, which made this possible, spurred for a short while a general feeling of optimism, even euphoria. Think of the good old times. That was the time when computers were seen as a revolutionary new technology, but a benevolent one, with the potential to change almost everything. In architecture, the potential to change the way we design and make almost everything. That optimism, in turn, fed the notorious dot-com bubble around the turn of the millennium. But even before the bubble burst in April 2001, many in the design professions had already started to develop a strong dislike for all things digital. The anti-digital backlash of part of the design establishment was strong and pervasive. And while a brief period of digital exuberance in the 90s famously produced a digital style of smooth and streamlined surfaces, known today as parametricism. It wasn't called that way back then, and today universally detested, but that's another story. Many who did not like that back then, including many well-intentioned defenders of the tectonic nature of building, rallied beyond a mighty scholarly work of Kenneth Frampton, first published in 1995, but that was in English, because it was first published in German in 1993. And it wasn't translated from German into English. Frampton wrote it into English, was translated into German, published in German, and then 2 years later, published in the original version by Kenneth Frampton. This book became, unexpectedly, a beacon, a guiding light, almost a manifesto for all who, for whatever reason, oppose the adoption of digital technologies in architecture. The culture war between digital technologists and anti-digital conservatives, which was very strident for a while, particularly around the turn of the millennium, then abated slowly in the 20 years that followed for many reasons. First, digital technologies turned out to be less disruptive than feared. And in fact, many digital tools soon went mainstream, pervading many aspects of the building and construction industry, but becoming, as it often happens in the process, a bit boring. And then, as we know, our priorities took the lead due to the rise of more urgent social, racial, and environmental issues. So the question of technology slowly faded in the background, and technology was almost put back on the back burner, where it had been throughout most of the 70s and the 80s, for example, when all of a sudden, a couple of years ago, the same culture war restarted afresh, almost as violent as in the 90s. And this is due, as we all know, to the explosion of a new breed of artificial intelligence called generative AI. And mind the date, October 2022, Silicon Valley new craze. That was in the New York Times, which sparked so much excitement, particularly in the financial markets. So much so that economists have suggested that we may now be experiencing a second dot-com bubble, similar in spirit to that of the 90s, implying that a new dot-com burst may also follow. This may well be so, both for the boom and the burst or bust part of the story, but times have changed. And while 1 generation ago, some degree of enthusiasm for the promise of digital technologies was general and widespread, today our cultural attitude is different. and we are all way more suspicious of all things technical and of digital technologies in general. Thank you, Elon Musk. Today, we tend to see artificial intelligence as a danger rather than an opportunity, not as a tool for us to use if and when needed, but as an enemy against which we should prepare a line of defense. This, at least, is the stated position of many of our government and institutions, including professional bodies. In architecture and design, too, alarm is widespread. And even in our schools, when we mention the possible roles of AI in design, students are more often worried than excited. In the 90s, it was the other way around. So the typical student question in our schools today is not what we can do with AI, but will AI steal our jobs? A short answer, no, it won't. But if we have the time for a slightly longer answer, let me start with a disclaimer. Of course, the technology is changing so fast, as we have seen in the last couple of years, that what seems right today may be proven wrong tomorrow. However, based on today's state of the art, this would be my argument today. Let's be practical. Let's try to figure out what AI is and what it is not. What is the technical logic of today's AI? Based on that, what it can do, what it cannot do, what it should not do. First thing to bear in mind, which is often the source of some confusion. Today's generative AI, the one that exploded 2 years ago, is being sold as a very new technology. But artificial intelligence is in fact a pretty old technology which has been around for almost 1 century now, at least 80 years. The term artificial intelligence was invented in 1956. The circumstances when it came to light are well known. A team of computer scientists organized a summer seminar at Dartmouth College, and they I was here, right? And they chose to call it a seminar on artificial intelligence to avoid any reference to Norbert Wiener's cybernetic and to Norbert Wiener himself, because they didn't want to invite him. Wiener, in turn, had minted the term cybernetics, just made it up, out of nothing, or actually out of Greek, but fake Greek. He made up even the Greek, to give a name to his new science of control and communication in the animal and in the machine. But Wiener's interest in human and animal physiology and neurology, particularly the neurology of cats, because he was putting electrodes into the brains of decerebrated cats to see what was happening. Most people found that a bit strange. And, so let's say he was not very popular with mathematicians and engineers, and Wiener himself, but by that time, had acquired the reputation of being somewhat of an eccentric. Unrelated to Norbert Wiener's cybernetic or cybernetic, the main outcome of the Dartmouth seminar was Marvin Sminsky's seminal paper, Steps Toward Artificial Intelligence, written in 1960, published in 1961, which outlined the mathematical principles of artificial intelligence in terms that held good until very recently. In fact, this paper was on the website of the MIT as a working paper until 2 or 3 years ago. In that paper, Minsky famously defined artificial intelligence as a general problem-solving machine. A machine that would solve problems, that was the idea, by massive trial and error. The formula is by heuristic programming and core search. A machine that would find the best solution by trying many possible solutions, one after the other, discarding some, keeping others, in a huge number of comparative trials, like A/B testing on steroids. The idea was evidently that computers could make a huge number of trials very fast. So they would find a decent solution within a reasonable amount of time. In the years that followed, however, it appeared that electronic computers of the time, even though they were evidently much faster than human computers, they were not fast enough to work that way. And that heuristic process, meaning trial and error, would still take too long. So already in the course of the 60s, a much less ambitious mode of artificial intelligence took the lead, where machine would not learn by trial and error, but would simply carry out scripted tasks based on rules, following a preset path of multiple choice options. This is known as knowledge-based system, rule-based system, or expert system, and this is basically as an ATM to this day still works. It's not rocket science, but it does its job. All the same, by the mid-70s, many observed that most artificial intelligence systems built to that date didn't work at all. And some concluded that perhaps artificial intelligence was not a very good idea from the start. So after the first AI boom in the 60s, this was the first AI bust, and the beginning of a period known in the histories of computer science as the winter of artificial intelligence. That was the 80s, when artificial intelligence basically did not exist. So much so that when architects began using computers for good in the early 90s to do something like this, is the late 90s, but the spirit of the same. The precedents of cybernetics and artificial intelligence, the 50s, 60s, and 70s were completely forgotten and did not play any role. For architects and designers that started experimenting with image editors, animation software, or spline modeling software in the 90s, computers were drawing machines, not thinking machines. The most popular software of the time were spline modelers, like this one in the first release. It was about streamlining or digital aerodynamics. This is spline modeling, and this is where it came from engineering, not from cybernetics. This landscape started to change well into the new millennium, when it appeared that, due to the technical availability of unprecedented and ever-increasing amounts of data storage and data processing power, known as big data and brute force computing, some early methods of heuristic problem solving, as Minsky had predicted, could become practically viable. This revival of the first and oldest mode of artificial intelligence, now called machine learning, is at the basis of the achievements of contemporary computer science. And artificial intelligence, which was infamously axed half a century ago, when many concluded it would never work, started to stage a revival of sorts, when it became evident that today's technology could actually make it work, sometimes unexpectedly well. For all that, the recent revival of artificial intelligence did not cross paths with the visual arts, let alone with computer-aided design, until at some point in the mid-2010s, let's say 2014, 2016, when it appeared that a new mode of machine learning called generative adversarial networks, or GAN, was particularly suitable to the manipulation of images. These are the two papers that started it all. That was the beginning of GAN art, by now a well-established staple of digital art, known, for example, from the works of Refik Anadol. I can't run the video, but it's probably still on the website of the MoMA. That was an exhibition in the spring of last year. Or German digital artist Mario Klingemann. Avant-garde designers, in turn, beginning in academia, started to experiment with GAN around 2019, 2020. And the first publications by Phil Bernstein, Stanislas Chailloux, Mattia Del Campo, and Neil Leach date from around 2021, 2022. The technical logic of GAN-based image processing is well known. It has been largely commented upon. GAN artists must first of all gather a collection of related images that are seen as pertinent to a specific project. This collection, which they call a data set, is then fed into the machine learning algorithms that ferret out somehow the commonalities among those images, finding and highlighting what those images have in common. The result of that inductive process is a mathematical matrix that computer scientists call a latent space. And here I always have to tell my students not to be led astray by the term is not a space. It has nothing to do with space, just a mathematical expression. They call it that way. They could have called it XYZ329. It would just work the same. But this latent space roughly corresponds to what philosophers would call the definition, idea, formula, or quintessence of the original data set. Example, if the original data set is a collection of images of dogs, the corresponding latent space is the quintessence, the definition, the formulation of what a dog is, or the image of an ideal dog, a super dog, in a sense. Once this definition has been achieved, and it is residing into the latent space, this definition can be applied to different tasks. The first is analytic, showing the system a new picture and asking, is this a dog? And the system will answer, that's a good match. 78% it's a dog, the rest we don't know. Or generative, asking the system to produce realistic images of dogs that do not exist. Fake dogs, these are fake dogs. Here the system is imitating the data sets of real dogs we have fed into the system. These are similar to the pictures of dogs into the data sets, as all the dogs in the data set are golden retrievers, so white dogs with a black nose. All the fake dogs are white dogs with a black nose. And then there is another possibility, combinatory, asking the system to merge two data sets in given proportions, producing, for example, pictures of a canine entity that looks 80% dog and 20% coyote. So on the left is 80% dog and 20%. When the percent shift and you go to the right, it is more and more coyote and less dog. So the picture at the right hand of the series, 80% coyote. It really looks like a coyote, and 20% dog. Now, there is an interesting variation in this combinatory mode, where generative algorithms, or GANs, are asked to apply some general aspects of a data set to a single individual, not to a set, thus transforming this individual into a new one that still looks similar to the example from which it derives, but at the same time shows some features of an external data set to which it is being assimilated. Not surprisingly, the computer scientists who introduced these processes of transformation and assimilation between an individual and a set soon started to call this operation a style transfer. The example, the term has stuck and is now in current use. Style transfer, and that's an example. Since they were all dogs, this is about cats. This is not a fake cat. I always have to say it. It's a real cat. I know him well. His name is Robin. A good cat. I would say an excellent cat. So this is a picture of a cat. a real cat, then the style into which we decided to import Robin is a historic style, is the style called neoplasticism or the style, which incidentally means the style. So that's a shortcut. And so we import Robin into the style of Piet Mondrian, and this is what Piet Mondrian would or might have painted if he had seen Robin around 1924. Style transfer. The tidal wave of generative AI that has swept the planet since the spring of 2022 has not much changed in this conceptual framework, but it has introduced some important technical innovations. Generative pre-trained transformers, or GPT in particular, have generalized the use of large language models, or LLM. Importantly, the data sets are now often composed, as we all know, of text and image pairs, couples, where images are labeled and described with words. Second, these new data sets, or data sets of text and images, are not custom-made or made for a specific task, as in the old GAN system. Instead, today's large language models are huge and generic. They are all-purpose data set, scraped, or in fact stolen, from all possible sources. User-friendly text-to-image or multimodal tools like Midjourney or DALL-E can create images out of verbal or visual prompts as if out of nothing. And their almost supernatural deeds have evidently impressed the general public. But the hidden data sets on which they are based derive from vast troves of labeled images taken from the public internet. And as such, they can only reflect what the internet has already gathered. In this sense, general-purpose AI tools like those I just mentioned only automate crowdsourcing by tapping the same collective knowledge that Wikipedia, for example, or other social media apps have been canvassing and soliciting for the last 20 years. Given this technical context, the miraculous images now served on demand by generative AI may be of some use to sociologists or advertising executives, but they appear at first glance, based on the current state of the art, of only limited interest to visual artists and to designers. For example, if I type the prompt Switzerland into DALL-E, what I get is in fact an automated visual opinion poll. This is what Switzerland looks like in the mind of most people. Now, if you have to design, the envelope of a new box of chocolate, you may have, you may use this. But as a designer, I fail to see what. Cross-modal image generators based on large language models function by the retrieval, aggregation, and averaging of precedent. And as the precedent from which they derive is a crowdsourced collection of images, generative AI is, in this instance, a machine that automates the imitation of visual commonplaces. This is the wisdom of crowds. This is the opinion of most, translated into one synthetic picture that is in turn dependent in full and exclusively on the data sets from which it derives. This technical logic applies to all applications of today's generative AI, not only transmodal or multimodal, but also, as some say, cheese model, meaning text to text or image to image. This is worth keeping in mind whenever we use generative AI chatbots to ask quantitative queries. We would typically answer following a formalized algorithm, mathematical rules, for example, or the laws of physics. In theory, if we ask an AI chatbot to calculate the result of 10 times 10, or what is 10 to the power of 2, The system would not calculate it arithmetically, as we learned in primary school, but would instead score an entire encyclopedia of recorded writing, but part of it can search, looking for any precedent of anyone having already carried out such operation, coming to the conclusion that the historically recorded social consensus on that matter is that 10 times 10 tends in most cases to be equal to 100. In fact, we must presume that most chatbots now include a shortcut to a calculator, so they would use it when needed. But given the logic on which they are built, this is how they would answer, in principle, quantitative queries, not by applying rules, but by searching for and averaging precedent. In this instance, looking for answers already given to the same question. But this is not mathematics, this is an opinion poll. Generative AI does not carry out rule-based calculations. It can only regurgitate common knowledge, insofar as this knowledge has been recorded and it is included in a dataset that AI can search. It follows from the above that generative AI, in spite of its miraculous image-making capabilities, cannot, for example, tie together the plan, elevation, and sections of an object, or build an axonometric view, or a perspectival view based on parallel or central projections, because such drawings would follow the formal laws of descriptive or projective geometry, which generative AI cannot apply as such. Plenty of traditional CAD software can work with geometrical projection just fine, evidently. Good old AutoCAD has been doing that for 30 years. But generative AI can, at best, only imitate a dataset of related drawings pertinent to the matter at hand, assuming this drawing exists and that they are included in the dataset on which it runs, or on which it was, quote-unquote, trained. As a result, bearing in mind that generative AI technology is changing so fast, as I already said, that today's remark can be obsolete tomorrow, some provisional remarks on what generative AI can and cannot do, or even shouldn't do, for the design professions can already be suggested, based on today's state of the art. First, while the generation of images based on generic data sets is of limited interest to the design professions, the surprising capacity of generative AI for identifying styles and transferring styles across context, this has many useful applications in many design settings. Many offices have trained a generative AI system on a data set made of their own work, thus creating a system capable of detecting and reproducing the peculiar style of that office, assuming there is one, of course. The creation of custom-made, curated data sets capable of detecting and imitating specific visual styles can serve many design tasks, and promising experiments are being conducted that would allow the combination in different percents of large language models and proprietary data sets in different proportions, as and when needed. This is often called fine-tuning. Second, and following from the above, generative AI, by the way it works, is fostering a revival of some traditional principles of Western art theory, like imitation and style, which, as we all know, were mostly abandoned by modernism in the course of the 20th century. Generative AI is a machine that automates imitation, the imitation of the data set we fed into it, the imitation of the data set it was trained on. But as it does so, it reminds us of the nature of creative imitation. Imitation is not a photocopy, it is not even just a copy. It is inspiration It is not identical replication, it is assimilation and transfiguration. When we use AI, all creation is a transfiguration of some precedent of choice, which is what computer scientists call a data set. It all starts with a data set. There is no generation without a data set. If the data set is made of dogs, well, it is dogs in and dogs out. But unrelated to computer science, plenty of other theories, old and new, and simple common sense, equally suggest that all expression, or to be precise, the communication of all expression, is based on a language we share with others. A language that exists outside of us, before we use it. Every word we use means something because others have already used it. Everything we write derives from something we have read. Everything we say derives from something we have heard. Every sketch we draw derives from something we have seen. Expression and communication alike depend on something that is already out there, something that pre-exists, something which inspires our thought and gives shapes to our speech. Hence, it would appear that for artificial intelligence and for human intelligence alike, the first step in every creative process resides in the awareness, acknowledgement, election, and selection of that pre-existing data sets that makes all expression and all communication possible. That is our precedent of reference and our reference to precedent. Precedent, that language, that code, that tradition into which we inscribe ourselves, that canon that gives meaning to our voice. For this is what generative AI teaches us and what we should remember when we use it and even when we don't. Nothing is created out of nothing. Everything is generated out of something which is already out there, generated out of that precedent that computer scientists call a data set, but which is in fact a carefully curated selection based on choice. Every data set is a canon, and every canon is a data set. When we work with pen and paper on our own, in a silent room without electricity, we may easily forget that we must have made or chosen our own canon at some point, so we may delude ourselves and think that there is no canon. But with generative AI, there is no way to cheat, because the technical logic of generative AI is brutally transparent. If it works, it is because someone, somewhere, must have made a data set, chosen a canon, chosen some precedents based on preference, our preference or someone else's, even when, as in the case of today's large language models, that selection reflects the choices and biases of a corporation, a community, a crowd, or a nation. And we know all too well this day that preference may lead to or come from prejudice. At the start of each creative process, someone must have decided to include something and to exclude someone. That is the iron logic of the data set, now and ever, regardless of the technology we use. That's the way canons or data sets work, and always did. This is the teaching of generative AI. We cannot create without a data set. We cannot escape precedent. How we chose, or how we choose to deal with precedent, however, was and remain our own individual choice. Never mind the technology we are using, it is a momentous choice for which we shall be held accountable. For let's not beat about the bush, precedent in architecture means tradition and history. And it is strange that we should need AI and computer science to remind us that all new act of design is inevitably based to some extent on precedent, tradition, and history. After all, some of us have been saying that for quite a long time. Third and last remark. the technical logic of generative AI has vast potentials beyond the domain of image generation, as the same notion of imitative style transfer, or indeed knowledge transfer based on imitation, could be applied to all sorts of data, regardless of visual implications. And indeed, various experiments, including this one by Google's DeepMind team, already suggest that imitative transfer, better known as imitation learning, or knowledge transfer based on imitation, could be a game changer. Imitation learning could, for example, help to automate artisanal practices entailing operations that do not depend on formalized rules or formalizable processes, like cooking risotto, for example. Try to do it on a rule-based system. It's impossible. In the building trades in particular, knowledge transfer by imitation learning could serve to replicate the kind of informal artisan skills that some have called tacit knowledge, meaning embodied know-how that cannot be easily spelled out nor transmitted via explicit rules. We may easily imagine that using machine learning, a robot could soon be able to scan an open field, pick and choose the best boulders for whatever task it was given, break and resize them if needed for geometrical congruence, and use all and only the resulting bits and pieces to build a close-fitting dry stone wall. This was defended in Zurich a couple of years ago. This was a big wall using a big machine, but I'm dreaming of a smaller machine to build a small wall using the same technical logic. And today, that robotic job wouldn't even need to be scripted. A data set of examples of local dry stone walls could be enough to train the model. Imagine that you are there, and imagine you can put together a data set featuring 1,000 examples of local dry stone walls. Now, evidently, they would all look similar, because that's the local tradition, distilled through centuries of artisan trial and error, based on locally available natural and human resources. Because the stone was always the same, and so for centuries was the way to use it. That regularity without rules, derives from a body of locally transmitted knowledge, acquired by experience and human proximity. And this is exactly the kind of expertise that generative AI could learn from a data set and replicate by imitation alone. Imitation learning. Imitation without rules. Imitation without formalization. This is how automated learning from observation could also replace the analytic methods of modern engineering by providing, in some cases, better means to the same end, even leading to solutions that modern rule-based deductive tools could not otherwise come up with. This is a project which was did in Shanghai, China, 2 or 3 years ago, the Dragonfly Wing Project. They built a data set of dragonfly wings, because in summer at Shanghai there are huge swarms of dragonflies that are everywhere. And so they easily built a huge data set of dragonfly wings. When by imitation, they extracted from this data set a huge number of variations of dragonfly wings, which no engineer could come up with or calculated analytically. They could double check them, of course, and some of them, surprise, surprise, could actually were a good match to design the rotor of the blades of a rotor of a drone. I don't think the drone ever flew, but the next time it might. And today, that robotic job, sorry, that already like that. So this could be the motto of the next step of engineering. When you cannot calculate, imitate. The next step, the next frontier. But this may look like, rocket science or something coming in the future, but let's look the other way. Is this not what pre-industrial artisans always did? before the rise of the mathematically driven quantitative methods of industrial modernity. Artisans of old used intuitive analogic tool out of necessity, because they had nothing else. That was the best they could do. This is the almost timeless way of building in the valley I myself come from, just 20 miles west of here, unchanged for centuries, because for centuries, both the stone and the people were always the same. Then industrial modernity came, and with it, alien, unprecedented materials and techniques. With them came formulas, handbooks, manuals, and instructions. And engineers trained at universities started to draft construction drawings, and on-site blueprints sent from far away replaced locally transmitted knowledge, oral transmission, tacit knowledge. As we know, that system worked very well for quite some time. But as we also know, that system has now almost stopped working. And we must urgently find some other way to make the things we need before the implosion of the old way of making ends in disorder and in disaster. 1 generation ago, the self-styled defenders of the good old tectonic order in building lambasted digital electronic technologies as the enemies of architecture, of humankind, and of civilization at large. Looking back at them from today's vantage point, it now appears that their crusade was at least in part prescient. Digital technologies are not the nemesis of civilization at large, but they are the direct opposite of one civilization in particular, that of industrial mechanical modernity, predicated on the unlimited exploitation of natural and human resources. The digital technologies by themselves did not bring about the fall of mechanical modernity. Mechanical modernity fell all alone. Karl Marx would have said that it fell due to its internal contradictions. Today, we may also add that it fell because it ran out of raw materials and fossil fuels. Whatever the causes, fall it did. And it does offer some glint of hope that just as the modern way of making is conspicuously failing us, generative AI appears to be offering a viable, automated, and scalable way of bringing some old ways of making back to life. And with them, hopefully, some of their ancestral physiocratic sustainability. Generative AI is not a spaceship. It is a time machine. Thank you.